This is a help video for the Laplace Nodal Solutions game in Circuit Tutor, Level 1. I'll go ahead and enter that game. Now this does presume that you've already completed the introductory tutorial, which is associated with the Laplace impedance simplification game, but actually covers all 4 of the Laplace circuit analysis games. So we'll assume that you've already looked at that, which has crucial information for doing these problems. So now we have the option of either looking at examples or exercises. It's always a good idea to look at an example to see how to work the problems. So let's pull up a typical example here of a level 1 problem. And so we have a problem here with an inductor, capacitor, and a resistor, and a sought voltage, and then we have a current source and a voltage source, both of which happen to be step function sources. So first we have to convert that problem into the Laplace domain, which has been done here. So the 1 amp source is now 1 over S, and the 4 volt U of t source is now 4 over S. So the source has been converted, and the impedances, the resistor, of course, stays the same. The 1 Henry inductor becomes S ohms, and the 2 farad capacitor becomes a 1 over 2S. Okay, so that's then the ground has been selected. In this case, it wants it connected to voltage sources and also to as many other elements as possible. So the optimal location for the ground here is probably this lower center node, which has been selected. And we've color-coded the nodes. And so now we write a voltage constraint equation. So for example, for the source, that fixes V2 at a value of just the value of the source, V1S, which is 4 over S. So that's written there. Then a KCL equation cannot be written for node 2 because it's attached to a voltage source whose current is whatever it needs to be, and we don't know that. But we can do it for node 1. So that's shown here. We have the 3 different currents leaving that node. So the current through the source here is the negative of that source value. Since that's 1 over S, that's minus 1 over S amps. Then through the inductive impedance, it's V1 minus 0, or just V1 over S, the second term, in the magenta. And then the third one is V1 minus V3 divided by the 5 ohm impedance, and that has to be equal to 0. And then I would illustrate the currents here for the next equation. So here we just have 2 currents leaving node 3. Again, we can't do it for node 2, so we'll do it for node 3. So through the 5 ohm, we have V3 minus V1 divided by 5 ohms with the appropriate polarity there, and then V3 minus V2 here divided by the 1 over 2S impedance. And then those equations are put into simplified form by collecting all the coefficients of V1. So the first equation, of course, is just this one here, the V2 equals 4 over S. Then this would be the second row, and so the V1 coefficients have been collected here, which would be 1 over S and 1 over 5. That's been put over a common denominator, so it's S plus 5 over 5S. V2 does not appear, so that's a 0, and V3 here is just minus 1/5, or it can be written in decimal form as minus 0.2. And then the right-hand side would be this constant brought over to the right-hand side, which is 1 over S. And then the second one, we collect the coefficient of V1. That would be negative 1/5, or negative 0.2 times V1. And then for the V2, you see it's just going to be this term, so it's going to be minus 2S, since the reciprocal of the reciprocal, of course, just gives us back the 2S. And then for the V3, we have 2 terms, so we have 1/5, and we have then 2S V3. And factoring a common factor of 2 out of that, that gives us the 2 times S plus 0.1 times V3. And then those coefficients are basically just copied over into the matrix equation, although I don't really recommend solving matrix equations for this type of problem, but it is possible if you wanted to do that. Then our sought variable here, V0, which, scroll back up, again, that was equal to V3 minus V1, as you can see here. And so that's written here. And then the solution would be solved usually best by starting with these simplified equations. In this case, we take the simple one, which is just v2 is vs, and substitute that into the third equation. It is not needed here. And that would give us two equations and two unknowns, namely v1 and v3. And then we could proceed as one normally does, either by multiplying by some constant through here to make the coefficient of one of these terms be equal to this. And notice that when doing that, we're going to need v3 and v1. We don't need v2 in this case. We already have, well, we have v2 actually, so that's the easy one. So we need both v1 and v3. So in this case, it doesn't really matter which one we solve for, but in any case, we can solve for both of those variables using these two more complicated equations after again substituting. And the result then is this. After being simplified, it's negative 10 times s minus 4 over 2s squared plus 10s plus 1. And then that's factored to bring out a, well, actually really just to make the constant in front of s squared be 1. It's a little bit more convenient that way for doing partial fractions. And then this has been factored using the quadratic formula here. And then put over a partial fraction, well, put into a partial fraction expansion, a over s plus 0.1021, and then b over s plus 0.49, excuse me, 4.898. And then we just do the inverse transform of that. So we have the 4.277 here, and 1 over s plus 0.102. Notice we have to put the time constant in the reciprocal, right? I'm sorry, in the denominator. So that's the reciprocal of this number. So the reciprocal of 0.102 is about 9.8 roughly. And then here we do the same thing. The reciprocal of 4.898 is the 0.204. And we put the coefficient out front, just using the standard table. And there's a table available here at all times of Laplace transforms, including the one for the case with complex roots down at the bottom here. And there's also, if you're getting help, you can also get the rational function syntax help, which I mentioned before. Okay, so that's the final result, and that's the example. And if you want additional explanations of the equations or the constraint equations and so forth, you can get that up here. Now, you can show Gaussian elimination steps. I don't really recommend doing it this way, but if you are bound and determined to do that, which is a little bit more complicated, it will show you the actual steps that Circuit Tutor uses internally to solve the problem. And as you see, there's quite a few steps here. And we start with the original matrix, then we switch rows 1 and 3, basically to make this be non-zero up here. And then we have to add a multiple of this row to this one to zero out that, well, actually a multiple of this row to this one to zero out the first entry here. So we're trying to block diagonalize it. And then we would do a similar thing here. We'd multiply, well, actually we'd rationalize this to be, actually in this case, I guess it's been switched to make that simpler. So we just switch those two rows, which may or may not make much difference. And then we would basically add a multiple of this to here, so multiply this times 2 times s plus 5. And then here it doesn't do anything. Here we have to add that, and that simplifies to this. So now we've block diagonalized, or really upper diagonalized this matrix, and now we can just divide this by this, as shown in the bottom here, to get the third variable that's substituted back into this equation. Well, actually this one solves itself because it's just v2 equals 4s. And then substituting those two values into the top equation, we get an equation for the first variable, and then that works out to this after doing the relevant algebra, which is not all shown here. Okay, so let's go ahead and do an exercise now at level 1. So here's our randomly generated problem. And once again, it's a second order circuit with one inductor and one capacitor. And the first challenge will be to convert this entirely into the Laplace domain. So we have to fill in these boxes in this copy of the circuit. Again, the resistor values have just been copied over since those don't change. We're just one resistor here. So 1 over SC is just, in this case, going to be 1 over S. And then the I1S of t, since that's a unit step function with a strength of 2, that'll just be 2 over S for the current source. And then for the voltage source, that's just V1S of t, so that's U of t, so that's just going to be, and I'm sorry, actually, yeah, 2 over S, and this is 1 over S. So, and then the inductive impedance, just 2 times S. And we've entered that now, so now we click on Done Converting to check that. If for any reason you did need a Laplace transform table, you can bring that up here. Hopefully you know the simple ones already, but if you need them, they're available again in that table. And of course you also have help and video help, which you're watching now. The help button again does offer you access to the rational function syntax, which you probably don't need here, but if you do need that, that's the help on entering the rational functions in Circuit Tutor. Okay, so we'll check that. That is correct. And now it's going to redraw the circuit for us in the Laplace domain. And it's going to ask us now to first select our reference node. Now remember that you usually want it connected to as many voltage sources as possible to minimize the use of supernodes and the like, and also to as many other elements as we can. So clearly the best one would be this one on the right here. This one would be not quite as good because it's only connected to one other element. So we'll put it over here, and then we'll click OK to finalize that. And it's just redrawn it a little bit here. Now we have the instructions as to what to do, which are similar to what you would do for a DC or an AC circuit, just except that we have to have functions of S now. And again, the rational function syntax help is available there if you need that. So now we'll start by entering equations. And since we're doing nodal analysis here in this game, we'll start by entering a voltage constraint equation. Since we do have a voltage source, we need to do that. And that's one of the simpler equations. So that will be, since this is our ground, that means simply that V2 is the value of this source. So we'll just select that term. You can click or drag here. If the clicking doesn't work, just drag it. And we'll fill in the blanks there. So that's going to be V2 is equal to the value of the source, which is just 1 over S. So now we would just type that rational function, 1 over S. And then we check that. And that's all the voltage constraints we have, since there's only one voltage source in this circuit. So now we'll go to KCL, which are sort of the core equations for nodal analysis, of course, since nodal analysis is based on Kirchhoff's current law. And we'll look and see what nodes can we enter a KCL equation for. Well, node 1, you see, it does not have any attachments to voltage sources, so that one we can do. So we'll click on that one by itself and select that. We select one or more of these. And now we have to add just 2 currents, one going out through here and one going out through here. Or if you prefer, you can do currents at enter. It doesn't matter. Circuit Tutor supports both. It will usually show currents leaving, but it can do either one. And in both cases, it's going to require a difference of voltages, node voltages divided by impedance. So we'll use that term. And then that's going to just add to 0. So we'll put that in here. Now we'll fill in the blanks. So for example, this one would be V1. Oh, I'm sorry, that's not a difference of node voltages. That one's connected to ground. So let me correct that. That should have been just this. So V1 divided by 2S. And here notice we've got a separate text box for the denominator. So here we don't have to enclose this in parentheses because it's in its own denominator already. And then for this current, that would be V1 minus V3. So we'll just fill in those blanks. And then the impedance is the 1 over S. So we just type that as 1/S for the division. Remember that you're not allowed to use negative exponents, so you cannot write that as S caret minus 1. Okay, so we'll check that. And then we need to do node 2 we cannot do because it has a voltage source connected, and in fact that's part of the reference supernode basically. So this is all the reference supernode here, and therefore we don't traditionally write an equation for that, a KCL equation. So we'll go instead to node 3, which is not connected to any voltage source, so that one can be done. And so now we have, again, difference of voltages. Here this is to ground, and here's a difference of voltages. So we'll need 2 of these and 1 of these, and that's equal to 0. So through the 1 over S, we're going to have V3 on the high side minus V1 on the presumed low side, divided by the 1 over S. And then for the 4 ohm, we're going to have V3 minus V2. So we'll just fill in the V3 and V2. And notice I'm using the tab key here, although you can't see it, to go easily between those blanks, which might speed you up a little bit if you use the tab key. And then that's a 4. And then, oh, I'm sorry, I wasn't paying attention. This is not a impedance, so that's just a current source. So we need a current source term there, a fixed current. And so that's going to be the negative of that value, which is 2 over S. So we're going to have minus quantity 2 over S. And you could make this a plus sign and put the minus sign in here, but that's probably the better form. It doesn't really matter. So we'll check that. And that is correct. And then finally we need to write our SOT variable equation for the SOT variable V0, which is this voltage here, which we can see is really just the same as V1 in this problem. And so we'll select the SOT branch voltage term type and just write that V0 equals V1. Very straightforward. So just fill in the 1 there, and that's all we need. And again, those are dimensionally consistent because they're both, of course, measured in volts. Okay, so that would be all the equations that we need to solve this circuit, and we can check that because we have 1, 2, 3 unknowns, namely the node voltages, and we have 1, 2, 3 equations, not counting the SOT variable. So that's the correct number of equations, so now it's appropriate to click No More Equations. And now it gives us instructions that we need to basically form the simplified equations by combining coefficients. And we could also multiply through by constants to rationalize it if we wish. Okay, so to do this, I'm going to just show you where I've done some of that on paper already. So first of all, the first equation is very simple. That just says V2 is 1 over S, so we just put a coefficient of 1 here, and then we put our 1 over S there, and the coefficients of V1 and V3 are the default zeros. Then the second equation, which we don't really have to put in order, but I will, just for simplicity. So now the V1 has a coefficient of 1 over 2S plus a coefficient that'll be basically S when we bring the 1 over S into the numerator. Of course, that just becomes S. So we write that as V1 over 2S plus S times V1 minus V3, that quantity, that's equal to 0. In this first equation, and now we have to put it over a common denominator. So we'll see that that's going to be just the 2s. So we multiply this by 2s over 2s, and so that'll give us a 2s squared for this term, for the V1, divided by the 2s. And then here we have a 1 over 2s, so that forms the 1 there. And then the V3 is just negative S V3, so write that over here. And that's now basically in our simplified form. So now we'll go ahead and enter that. So V1, we need an expression now, so we have to use parentheses in the numerator to make sure that everything in the numerator is being divided by the denominator, otherwise that wouldn't be the case. So we'll write 2s squared using the caret key for the power plus 1. It does not support double asterisks if you're used to using that, as some computer languages do, so you have to use the caret key. And we close the parenthesis, put the slash there for the denominator, and again, absolutely essential to have the parentheses around the 2s, otherwise we'd be dividing by 2 and multiplying by s using the standard PEMDAS order of operations you learned in algebra. So we need to make sure that if we intend to have the 2s in the denominator, we do enclose it in parentheses or square brackets. Either one will work. And also notice that the polynomial is written in descending orders, descending powers of s in standard algebraic notation. If you don't do that, it'll tell you have to reorder it. It won't count as an error, but you'll have to reorder it. Okay, so that's that term, and then the other term is minus SV3, so we just put a minus S there. Very simple, and the right-hand side is 0, so we leave that alone. And then this next equation, we have V3 minus V2 over 4. I just wrote it in a different order here. And then here I'll just bring the S upstairs, so that's S times V3 minus V1 minus the 2 over S equals 0. And now collecting the coefficients of V1, well, that's just going to be negative S here. So we write negative S V1, and V2, that's going to be only this term, so that's minus 1/4 or minus 0.25. You can enter it as a fraction if you like, but I've just written it that way. And V3 then, we have a 1/4 plus an S, and so that's just S plus, again, I could write it as 1/4, but I've written it as 0.25 here. And that's times V3, and then we bring the constant term over to the right-hand side. So we bring that, add 2 over S to both sides to bring that here. And it does involve S, but S is considered to be a constant for purposes of this type of algebra, because it's basically just a variable. Okay, so now we'll enter that, and we have negative S there for the V1, and then we're going to have minus 0.25 for V2. I like to put a leading 0 there to make it easier to read. And then for V3, it's going to be S plus 0.25. And then the right-hand side is going to be the 2 over S. Now we're free to multiply through if you prefer to rationalize these things. You can multiply through by any constant, which could include S, or actually any expression in S. I've just done it directly like this for simplicity, but remember, if you do, of course, multiply through, you have to obviously multiply every coefficient by the same thing for that to be correct. Okay, so now we'll check what we've done there, and that is correct. And now it just says we have to do a matrix equation. Now, again, you could re-enter all that stuff, but what's much easier, of course, is just to copy it from the simplified equations. And notice, by the way, on both this form and the previous one, you did have that rational function syntax help. Again, I'll just pull that up to remind you what that looks like. But basically, that's just the little cheat sheet that shows you the rules for entering rational function syntax here. And what you can enter is in the green here, and what you are not allowed to enter, things like that, are in the red. And so most of the time you probably won't need this, but if you do, you can look at this to see kind of what the rules are for doing that. Okay, so I'll close that, and oops, bring my thing here. Okay, so what I'm going to do is just copy that automatically by clicking that button. I could multiply everything, or multiply each row by a constant if I wanted to, but I'm not going to bother here. And then we'll just check that. And again, I don't really recommend working with matrices in these types of problems, but you have the option if you want to do that, as you did in the DC and AC cases. Okay, so it just gives you some instructions here. Asks you to keep your algebraic things for the record. And now okay, so now we have to solve, and this is, of course, where most of the work comes in, is actually solving for V1, V2, and V3. Well, the V2, we know that's easy. We can just enter that right away as being 1 over S. But the V1 and V3 are going to require some calculations, as I said, usually using this. And so I'm going to pull up that now. And put that over here. We can see a little bit better. Okay, so basically using these simplified equations that are shown here. So first of all, we know that, and we already wrote them out here. So the V2 is just 1 over S, as we already said. We entered here. And so we can substitute that in. Now it's not needed here, but in the second equation it is. So I write negative SV1 minus 0.25. Now this is just 1 over S, so that becomes negative 0.25 over S, plus S plus 0.25 times v3, and then we have 2 over s. So just basically substituted for v2. And then I just simplified that by combining the constant terms here. So I have minus SV1 bar plus the s plus 2.25 v3 bar. And then I just brought this over to the right-hand side, and since they have the same denominator, that's simple, just to add up to 2.25. Or if you like, you could write that as 9/4. Either one is fine. Now, we have 2 equations and 2 unknowns, namely this equation here and this equation I marked number 1 up here, both in v1 and v3. So we can solve those by any method you would normally use in conventional algebra to solve a 2 by 2. So we could, for example, solve for either one of these variables in either equation, really, and then plug it into the other equation, and then you have one equation and one unknown. Or I could multiply one of the equations of your choice. For example, I could multiply this one by this divided by minus s, so that would be minus 2s squared in the denominator. And basically, after doing that to each term, then I could just add the equations to eliminate v1. Now, if we want to be a little strategic, notice that what we really want in this problem is v1. We don't care about v3 because that doesn't come into our sought variable. So it would make a lot more sense then to get rid of v3 and solve for v1, as opposed to doing it the other way, which would be a little bit more work. It would give us both voltages, but we don't necessarily need that. And of course, if you want to enter all 3 here, then you do have to get both of them, but we can skip this step too, so I'm going to actually skip it. Okay, so let's solve this for v3. And so we basically put this term over on the right-hand side, and then we're going to divide by the s plus 0.25. So this term will just become SV1 on the right-hand side divided by the coefficient of v3 bar, which is s plus 0.25. And the constant becomes that value again divided by the coefficient of v3 bar. So that's it has the original s and then the s plus 0.25. So there's an explicit solution for v3 in terms of v1. Now we can plug that back into this equation. So where we see v3 bar here, we'll just place this expression. And so we have still this first term unchanged, v1 bar 2s squared plus 1 all over 2s. And then we can bring the SV3 bar over to the right-hand side, really, just for convenience, and multiply this times s. So we'll have s squared v1 bar over s plus 2.25, and then here we'll have 2.25 s divided by the s plus 0.25. And of course, I could have just canceled out those s's right away. I chose to do it down here instead, just because they're common to both sides. So now we basically we'll take and collect all the coefficients of the v1 bar. So over here we have the two, we're going to look at the common denominator of those 2 terms involving v1 bar, so that's going to be a 2s times an s plus 0.25. Those are our factors. And so there's our common denominator, the 2s times s plus 0.25. And then here we're going to have the 2s squared plus 1, but we need to multiply by s plus 0.25 divided by s plus 0.25 to put it over the common denominator. So we'll have that there for this term. And then we'll subtract this term from the left, and then that would be minus, and we have to multiply by 2s over 2s to again put it over the same common denominator. So that would give me a minus 2s cubed when I bring it over to the left times the v1 bar, and then the same common denominator. So now I've got this, and I can now observe this is what's left on the right, and so I can see, oh, I've got the s and the s plus 0.25 in both places, so it would be very convenient just to cancel those out. So always simplify your algebra as quickly as you can. Again, I didn't cross out these s's, but worked out the same. So now I need to multiply this out, since this is one case where you do want to distribute in, even though normally the goal is to factor, but if you're adding polynomials, you do need to distribute in so that you can simplify. And so just multiplying this out, we have the 2s squared times s is 2s cubed. Then we're going to have the 0.25 times 2s squared is 0.5 s squared. And then the s times 1 is just s. And the 1 times 0.25 is 0.25. And then we're still subtracting the minus 2s cubed. And then we're going to take this 2 and multiply it over to the right-hand side. So the 2.25 becomes 4.5 s here. And now I notice that the 2s cubed minus 2s cubed, that cancels out, which is nice, so we don't have to factor a cubic equation. Now sometimes you will have to factor a cubic equation, and there is a, in the introductory tutorial, for example, I give you an example of a website that's good for doing that, or you can use your calculator, you can use various techniques, but just make sure you use a good technique to get the roots. But in this case, I don't need to do that. So now I can solve for v1 just by dividing here by this coefficient and putting it in simplified form. Again, I've multiplied by the, well, I'm actually going to multiply through everything by 2 over 2 also, just to simplify things. Since this has a 0.5 s squared, I'd like that to be 1. So I multiply this by 2 and this by 2. So I have 9s in the numerator, and then this will be s squared plus the 0.5 s squared times 2 comes down to the 2s, and then the 0.25 times 2 becomes 0.5. So the s becomes 2s rather. Okay, and that's the solution for that. And that's also equal to v naught. Notice here. So what I'm going to do is just, so I don't have to basically calculate v3. I mean, I could do that if you want by substituting back into either of these first two equations, but in this case I don't really need to do it, so I'm just going to skip that step. It just means I'll get a little bit less feedback, but okay. And it also tells me now that because I'm going to do the sought variable, I do need to factor any quadratic or higher order terms in both the numerator and the denominator. That's, the numerator is really just so we can cancel out common terms. The denominator is so that we can do partial fractions that are going to be necessary in the next step. And so it just advises me that I need to factor things. So that means I can't enter it this way, so I'll have to first factor it. So the denominator is a quadratic, so I use the quadratic formula. Remember that if you have ax squared plus bx plus c equals 0, my preferred form of the quadratic is negative b over 2a. So in this case, that's going to be negative 2 divided by just 2, since a is 1 here, and then plus or minus the square root of the b over 2a quantity squared minus c over a. And so that's just, well, negative 1 squared is the same as 1 squared. The sign doesn't matter because we're squaring, and subtract the 0.5. And so simplifying, that's just negative 1 plus or minus the square root of a half. And so just working that out on a calculator, that's minus 0.292 and minus 1.707 inverse seconds. The inverse seconds is just a unit. Remember that because it's e to the st, s always has units of inverse seconds. Okay, and notice also we can tell right away what type of damping the circuit has, because these are both negative real roots and they're distinct. That, as you may remember, implies that the circuit is going to be overdamped in the time domain, so that we can kind of anticipate already. Okay, so now, and just be careful doing the arithmetic here, because sometimes people make mistakes with that. Okay, so now remember that a couple of things. First of all, it would be incorrect to write s minus 0.292 down here, as people sometimes want to do. But again, this needs to be a root. That means that if I substitute this value into here, it needs to make it 0. And clearly, if I were subtracting that value, it would not make it 0 at all. And so that wouldn't work. And likewise for this term, I have to have s plus that value, or, well, s minus this value, rather, which means s plus 1.707. Again, if I put this in there, this needs to make this 0, right? Because these are supposed to be the roots of this quadratic, and they wouldn't be otherwise. So we have to make sure we use the right signs there. The other thing I'll point out is that if you had not made this coefficient be 1, as I did here, which is probably a recommended thing to do, but if you had left that as being something other than 1, remember that an expression like this would never equal that, because the high power here is s times s, which is going to be s squared. So if you had some term here, say you left that to be 2 or something, then you'd need to put a 2 here as well, right? Because otherwise, these factored form would not match this. And so you always need to make sure, because that's a very common error that people make, is they forget about those constants, and you need to put that in the front to make sure that this in fact equals this. Otherwise they would not be equal and you'd have the wrong answer. Okay, and so again, just keep in mind those two very common errors, the signs here and making sure that if you do have a coefficient that's not unity here, that you put in the appropriate constant here, which you could then, of course, simplify with the numerator if you like. Okay, so that's our factored form. So now I'm going to enter that here. So I just type 9s. I don't need parentheses there because standard order of operations will take care of that anyway. And now I'll use square brackets to enclose the entire denominator. So I'll go s plus 0.292. Again, a good idea to type those leading zeros. And then parentheses, and then the s plus 1.707, close parentheses. And then we have to close the square bracket. Now, keep in mind, if I had left out the square brackets, this would not be right, because then I'd be dividing 9s by this first term, and the second term would get multiplied, meaning it's going into the numerator now. So you don't want that, so you can use the square brackets. Or you could do like you do on calculators, and instead of using brackets, put a second division sign in front of the s plus 1.707. It'll also accept that. But make sure that you do respect order of operations, because again, that's a very common error that people make. Okay, so we'll check that. And again, if you wanted to go back and check your node voltages because this wasn't working out, you could go do that. You can get your rational function syntax help if you need it here. You can give up at any point in the problem if you have to. And also you can get the instructions again. Okay, so we'll check that. And that was correct. And that's been printed now on the screen. And the next step then is to do the partial fraction expansion, which is the reason we needed to basically factor that to prepare. And keep in mind, you're not entering the time domain right away. Sometimes people want to enter the time domain expression, but that will not be accepted because, in fact, you won't even have the option to do that. Okay. Well, that shouldn't have happened there. That looks to be a bug that I'll have to fix. I'm going to bypass that for right now since that shouldn't have happened. And I'll check that and see what happens. Okay, so I'll have to get that fixed so that doesn't happen. Okay, so again, well, it's going to make me re-enter that thing for some reason. Okay, so we'll have to do that. Okay, so now we're going to do the partial fraction expansion. You should have gone straight into this, so we'll have to look into that issue. Okay, so now we select the partial fraction expansion. And now is going to be v naught of s equals, and we need to have multiple terms as we determined here. So let's go through the partial fraction expansion on paper first. So we have v naught of s equals 9s over s plus 0.292 times the quantity s plus 1.707. So we set that equal to a fraction involving the first term and a fraction involving the second term with unknown coefficients on the top. And then we can use the Heaviside method, or the method of residues, to compute a and b. Instead of cross-multiplying all of this, as they sometimes teach you to do in math class, and equating powers of the coefficients and getting a simultaneous set of equations, it's much easier just to really multiply both sides by s plus 0.292 to find a. That will cancel out this term here, and then we set s equal to minus 0.292 so that that corresponding term over here will become 0 and get rid of this entire b term. And so we are left with nothing but a here. And again, this is canceled out. So now we just plug in the value of s that we were substituting, which is minus 0.292. And then this term is gone, so we just have minus 0.292 here plus 1.707. And then just doing the math there on a calculator, that will give us minus 1.864. Then for the b term, we do a very similar procedure. So now we multiply through everything by s plus 1.707 and set s equal to the negative of that so that that becomes 0. So it wipes out this term basically. And then it cancels this term. And then we just have b, so all that's left on the right hand side, equals 9 times the value of s now, which is minus 1.707, divided by, here we substitute s again as minus 1.707 plus the 0.292. The second term is gone, so we don't show that. And then we just do the math here, and that works out to be 10.86. And you can see that, that makes sense here because you're these are different, so this gets smaller than the 1.707 because they have different signs, and therefore it's something that's going to be a little bit bigger than 9, and it is. Okay, so we'll need two terms there, and so I'll just select two of those term types. And those both have to have units of volts, so the amps, volts, watts thing, that's to select the units of each term. So you just type the V's there. And then here we have separate text boxes for the numerator and denominator, which is different from some of the other forms. And so here my A is going to be a negative tab over to 1.864. Oops. 0.864 divided by the S plus 0.292. And again, I don't need parentheses now because it's in its own box, so it's already dividing the entire thing. And then here the second term is going to be the 10.86 in the numerator, and it's positive this time, and then we divide by the S plus 1.707 as we had in our partial fraction expansion here, basically just putting these values of A and B into this formula. So we can check that now. And again, you're not trying to do a time domain here. You're doing still the partial fraction expansion. Okay, so that is correct. And so now we've done all our partial fraction equations. We just type no more equations. And it tells you the next step is to do the inverse Laplace transform in the time domain. And it also reminds you that you have a table of Laplace transforms that's going to show up as soon as I click that button. In fact, it's highlighted in yellow here. So if you need your inverse Laplace transforms, you can pull them up here. Again, this one for the exponential, hopefully you've already memorized anyway, but it's just e to the minus at u of t. The inverse transform is 1 over s plus a. And if you needed any others, you can scroll down to get to ones you need. Okay. All right, so now we select the only equation type, which is inverse Laplace transforms, and it's just reminding us that there's actually two sets of terms here. You might need some that there's not room to display here, so then you click on the term set 2 to get those. So I'll just illustrate that here. So there's an additional term involving a pure cosine function and a power law function, which you might sometimes need if it's critically damped, or if there's a cosine forcing function. So now I'm just going to enter that slot variable, and now I need to multiply everything by the u of t in the inverse transform, and so I'm going to put brackets around it. And I don't have any constant term, as you noticed. It's all the exponential terms because we just have this form. There's just two terms, so those both are going to give us exponential terms like this. And then I'm going to close the brackets here so that I can multiply the entire thing by u of t. And then that also provides for the units here, which, because this is a voltage, of course, that's going to be volts. And we don't have an option for millivolts or anything, but you won't need it for these problems. Okay, now the exponents, very importantly, need to be negative because we don't want our solution blowing up in time. So I'll just enter those right away as both being negative. If you leave that as the default positive, that's going to be incorrect. And the time constants are not allowed to be negative. Now notice that this does not have the form of a constant times e to the minus at. Instead of using the a, which is a rate constant, which would have units of inverse seconds, it's asking you to actually enter it in the denominator. And that's for consistency with the other games that we did, for example, in transients, where you entered time constants rather than rate constants. So that means I need to take the reciprocals of my two rate constants. So the 0.292, that's inverse seconds. So I take its reciprocal to get seconds. That's 3.414 just on a calculator. So that'll be the first one here, 3.414. And then the second rate constant is the reciprocal of the, the second time constant is the reciprocal of the second rate constant, which is 1.707, which is inverse seconds. And therefore, just doing that on a calculator is 0.5858. Again, just carrying through 4 digits just for sake of accuracy. we probably don't need that many. And then the first coefficient here we had found was the negative 1.864. And then the second coefficient here was the positive 10.86. So that should be our full answer in the time domain. So I'll go ahead and check that. And that is correct. And it's been printed on the screen here. And we can scroll down. Of course, you won't have the cheating things when you do it, but basically it has printed it, and now all we have to do is type no more equations. And that completes the problem. And it's going to generate a transcript, which you can review if you need to study or for any other purpose. And after you finish, there's just one problem required on this level. So after we finished, you can get a detailed explanation if you like here. So I'll opt for that here. And basically now it shows it as if it were an example. So it shows all the steps, including conversion from the time domain to the frequency domain. And it's going to do it kind of its own way now. It won't necessarily, it will choose your choice of reference node, but otherwise it may do things slightly differently than you did it. But it's a valid way. And it shows all the steps, including the partial fractions expansion, the inverse transform, and everything. And again, you do have that option if you like to see the Gaussian elimination steps, which I won't bother to show here. Okay, so I'm just going to close that out, and that completes the level 1.